So here we are, 3.5. It's entitled F, F prime, and F double prime, the three amigos right there. If you know the values of those three guys at any point, at any x value along your way from left to right on the graph, you know what the graph actually looks like. Because F tells you what the y values are, so you know where you are vertically. F prime tells you if you're increasing or decreasing, whether those y values are going up or down on an interval. And F double prime, of course, tells you the concavity, the curvature. Is it concave up like a cup, concave down like a frown? All right. Now notice that each one of those also is the rate of change of the previous. So if you want to know how fast the y values are changing, that's F prime. If you want to know how fast the slopes are changing, that's F double prime. If you want to know how fast the concavity is changing, that would be what? F triple prime, which we don't even really look at, okay? It's hard to manifest that on a graph. So it's kind of like in physics, you have your kinematic equations. You have essentially your position equation. You have your velocity equation. I'll just call it VEL. And then, of course, you have the acceleration equation. So that's really what we're looking at here, but we're looking at it non-contextually, just on a graph. You have your position. Where are your y values at a given moment? Your F prime, is it increasing or decreasing? What's the rate of change? What's the y value's velocity as they move from left to right? And then the concavity is the acceleration. Are the velocities increasing or decreasing? Are they curving upward or curving downward? So this little table right here just kind of summarizes everything, and I'm not going to read it to you. You're welcome to read it on your own. This little diagram is what we completed in the previous section. It looks like the zero is kind of hidden. But there you go. If you know the sign of the first and second derivative, of course, on any interval, it's going to be one of those four arcs. And, of course, if you combine it with the y values, you then know exactly where to put that. But typically what we do is we know the y values at the endpoints of these arcs, right? Because those are going to be either critical values or inflection values. And so it comes down to just like filling in the graph with these curves by connecting the dots, but not with straight lines. All right, very quickly here, example one, kind of putting it all together. I'm not necessarily going to ask you to do this, but there have been times on AP exams where free response questions have asked you to do something like this. Sketch a possible graph of a function that satisfies the following conditions. So it's a matter of interpreting math language into like instructions for yourself. It says f prime is greater than 0 from -1 to 1. What does that mean? Increasing. Good. So we know the function's increasing to the left of 1. So here's how I would do something like this. I would go ahead and get a graph started, coordinate grid. Here's x equals 1 right there. And if I know my graph is increasing, with a pencil I would do very, very faint strokes. Here I'm going to use a yellow, and I know that it's going uphill. So I just drew a yellow line, just to show the trend of what's happening. It's going uphill to the left of 1, something like that. The second part, it says f prime is less than 0 from 1 to infinity. That means the graph is going downhill or decreasing to the right of 1. So again, a general trend, maybe something like that. I can come in and fill in with the curvature, maybe if there was some concavity information. Now, it doesn't say anything about these two guys having to connect necessarily, and it doesn't necessarily say up above that it's a continuous function. So I'd have some options later. Second line, second derivative is positive to the left of -2. What does that mean? Concave up, all right, to the left of -2. So -2 is now an important x value. There's -1. Here's -2. It's going to be concave up. So here I'm going to use kind of a faint green now. I already know it's increasing. Now I know it has to be concave up. Well, there's only one way to do that, something like that. So now I can improve upon the yellow. It's also going to be concave up to the right of +2. So +2 is another important value. And it's concave up there, so using that light green again. I know it's already decreasing there, but now if it's decreasing concave up, it has to be something like, it has to be something like this. Decreasing concave up. something like that. And I'll connect them here later. Next piece, f double prime is less than 0 between -2 and 2. That means it's concave down. Okay, concave down. So I know it's got to be increasing concave down, and then I know it's got to be decreasing concave down. So once you have that, you can kind of erase the yellow or get rid of it, however you want to do it. And now we kind of have the green. Now again, it doesn't say anything about them needing to be connected. So if you wanted to, you could make this graph kind of disjoint at this moment. And now we go down to the last piece. It says the limit as x goes to -infinity is -2. What does that mean? That is the left end behavior. And we have to get closer and closer and closer to y equals 2, which means there has to be a what at -2? A horizontal asymptote. So if you want, you can now say, okay, this, you can draw that in there. What you can't do, you got to be careful here. If you put -2 a little bit higher, you can't put it right there, because then your graph, the way you have it drawn, would have to turn around and come back up. And that's going to change the increasing, decreasing, and the concavity. So it has to approach it in the same way that you have it going down. So if you haven't drawn -2 yet, just draw it right there. And now you can extend that light green line and say, okay, that looks great. And then the last piece of info, the limit as x goes to infinity is 0. That's the right end behavior, which means it has to do what? Get closer and closer to 0. Okay, well, 0 is the x-axis, right? Uh-oh. If I keep my graph like that, I'm going to have to turn around and come up. And that's going to make it now increasing and concave down, and it needs to be decreasing concave up everywhere to the right of 2, so I can't do that. So guess what I need to do? I need to adjust my graph. Okay, so if you're working with notability, not a big deal. We'll just scoot the whole thing down, and I do need to now modify it a little bit. I need to make this come down here to 2, and then still be decreasing concave up, but just kind of turn it a little more sharply towards the x-axis. So some slight modifications. And if you know that's what your final graph now is going to look like, you can just maybe trace over it darker or maybe with a different flavor. Okay, and there you go. That's all you have to do. It's kind of nice to maybe mark the points at 2 and -2. And I guess the way we have it drawn through a continuum, we would have a what at x equals 0? A horizontal asymptote and a local max. Good, because you can see up here, notice f prime changes from positive to negative at x equals 0. And we already determined it's concave down there. So by the second derivative test, if you make it continuous, you can have a local max there. Okay, excellent. Answers might vary because, again, it didn't say it was continuous and we're just looking on open intervals. You could throw some holes or discontinuities in there, some jumps, but there you go. Well, notice we say that to the right of 0, f prime, I'm sorry, 1 would be a critical value. I'm sorry, my bad. Thank you so much. 1 would be a critical value, not 0. 1 would be the critical value. And I didn't have it quite drawn like that, so maybe I should modify this piece to look more like this. Yeah, I should have had a solid dot there already, and not at 0. And then it would come down like that to 2. It's nice to put solid dots at those x values where either your slopes change signs or your concavity change signs. I threw myself off there by not putting a dot at 1. Okay, so yeah, 1 would be the local max location, not 0. Okay, awesome. Moving on to example 2. This is going to be 2 and 3 are very similar, and this again ties in what we did yesterday. It says the graph above is the graph of f. What's the graph above? The graph of f, not f prime. Okay, a little bit different. So depending on which graph you're given, you need to use it differently. Part A, on what open intervals is the function both decreasing and concave down? You could assume that the dots that I have there are going to be the inflection values, because those are hard to read. So we'll assume that 3 is an inflection value, -1 is an inflection value, -5 is an inflection value, okay? Where is the function both decreasing and concave down? Yeah, -7, -5. If you want to draw it first, decreasing concave down has to look like that. It's going to be on this little piece here. And is there another piece? 2 to 3. Good. So you could just answer that. -7 to -5, union 2 to 3. Okay? Piece of cake. You know what you're looking for. On what open intervals is the function both increasing and concave down? Well, increasing concave down looks like that. So where's the graph doing that? -1 to 2. Anywhere else? No. Notice this one doesn't say to justify. At what value or values of x does f have inflection points? Well, that's where the curvature changes. I told you to assume that the dots were the inflection values. So it changes from concave down to concave up first at x equals -5. And then it changes from concave up to concave down at -1. And then it changes from concave down to concave up at 3. And then to the right of 3, it's concave up. So again, you're looking for parts of smiles and parts of frowns. Anytime it changes from smile to frown or frown to smile, it's going to be an inflection value. All right, on what open intervals, if the graph above, part B. We're changing our mindset now, okay? That was part A. Part B, if the graph above now represents the graph of f prime and not f, now we're using it again, but we're treating it differently. Now on what open intervals is f increasing? -7 to -5, -1 to 5, and then 5 to 7. And you can actually step right through 5 because it's a single point. So remember, we're looking to see where the graph is positive or at least non-negative at a single point. Okay, 5 would be a stationary point like x cubed. We can go right through it. So we could say the function is increasing from -7 to -5, union -1 to, if you wanted to step over 5, it wouldn't be wrong, okay? And notice it didn't say to justify, but you could say that f is greater than or equal to 0 on this interval because you're including 5, greater than or equal to 0. At what value of x does f have a local minimum? Well, if this were the graph of f, a local minimum would be at x equals -3 and x equals 5. But now we're treating this like the graph of f prime. So a local minimum only occurs at a critical value. Your critical values are where f prime is 0. So -5, -1, and 5, and there's no places where it's undefined. So local mins now are where f prime changes from what to what? Negative to positive. So we need the graph to cross from low to high. That's going to be at -1. Okay, at x equals -1, and the justification would be since at this point the f prime changes from negative to positive. On what open intervals is our graph concave up? F concave up. Concave up. Now we're looking to see where the graph of f prime does what? We're looking at the what's of f prime now. If we're talking about concavity, slopes, and if we want it to be concave up, we need the slopes to be positive, so we need the graph to be increasing. So there and there. So from -3 to 2 and from 5 to 7. I'm not going to write them down. We're kind of going fast today because we're using it as a review. -3 to 2, 5 to 7. At what value of x does f have an inflection point? An inflection point is going to be where the second derivative changes signs. That's going to be where the slopes of f prime change signs. And remember, that's going to be the local max or local mins of f prime. So that's going to be at x equals what? -3, 2, and 5. Okay? Where the signs of the slopes of f prime change from positive to negative or negative to positive. The local max or mins. All right. So far, so good? That's reading it now as if it were the graph of f prime. Now we're going to read it like a way we haven't read it before. We are now going to pretend that that's the graph of f double prime. Oh boy. So now the y values are the concavity values, and the slopes are the rate of change of the concavity, which are kind of meaningless to us. Oh boy. Okay. We're kind of limited now in the questions I can ask. On what open intervals is the function both concave down? Let's get rid of the word both. We don't need that. On what open intervals is the function concave down? Well, the function is going to be concave down when the second derivative is negative. -5 to -1. That's it. It's just where the graph is negative, because that's the concavity graph. At what values of x does f of x have an inflection point? F is going to have an inflection point when f double prime changes signs, which is going to be at -5, -1, and that's it. What are the PIVs? The PIVs are where f double prime equals 0 or DNE. That's going to be -5, -1, and 5. But remember, like on the quiz, at 5, there's no sign change. It's positive on both sides. So the only actual inflection values are -5 and -1.
That's where f double prime changes sign.
Yes, that's where f double prime changes sign. And remember, if you had to justify, you would have to say how the sign changes. So it would require two sentences. Since f double prime changes from positive to negative at -5 and negative to positive at x equals -1. Okay, so if you understand that, you're in good shape. Same graph, reading it three different ways, okay, to get what we want. Same graph, example 3. The graph above is now the graph of a function f. On the same set of axes, sketch and label a possible graph of f prime and f double prime. So I'm using the same graph. We want to sketch f prime. How are we going to sketch f prime? Well, we're going to analyze the slopes of this graph, and we're going to draw a function whose y values represents the slopes. So we're going forward. We've done this already this year. The first thing you look for is where the graph has slopes of 0. That's going to be at -3 and 2. Okay, so that's going to be where your function f prime has zeros. Oh, and 5, yeah, and 5, yeah. I was going to do that, yeah, thank you. No, that's good, that's good. So there's actually 3. There's 3 places where we have horizontal tangents. So those are the x-intercepts of f prime. Now you analyze the slopes. Notice to the left of -3, our function is decreasing, yeah? So you're going to have negative y values. So it's going to be coming in like that. Between -3 and +2, our function is increasing, so the slopes are positive. Now, right here at the inflection value, which we assume is -1, that's going to be where the slopes are the most positive, where they're the steepest in the positive direction. So that should be the maximum value of f prime. And they're still positive, but now they're approaching 0 again. Okay, so they come up here, they're the steepest, right there, and then they start flattening out again towards 0. That's just where I have it marked. We're assuming that -1 is the inflection value. So that's going to be right there where you see your slope is 0 here. So that's why the y value is 0. As I move to the right, my slopes are getting bigger and bigger in the positive direction. If that's the inflection value, that's where the slopes are at a maximum. So right there is where it's the most positive. So that's going to be my absolute max of f prime. Because look what happens to my hand after that. After that, they're still positive, but now they're getting smaller, approaching 0. So I go up to a high point at -1, and I come back down towards 0. Okay? Now, same thing. From 2 to 5, my function is decreasing. But where is it decreasing at the fastest rate? Right there at 3. That's the inflection value. That's where it's the most negative. So as I go down, that's going to be just as low as I go, right there. And then I start coming back up towards 0. So the inflection values of f become the local extrema of f prime. We said that, but we said it the other way around. The local extrema of f prime are the inflection values of f. We're just using it in reverse. And then finally, to the right of 5, it's increasing at an increasing rate. So there you go. That could be the graph of f prime. Now, we could sketch the graph of f double prime. Let's do that real quick. If I'm sketching the graph of f double prime, I'm actually now sketching the derivative of what I drew, yeah? Now notice that my graph that I drew, f prime, kind of looks like it could be what degree polynomial? It has 3 x-intercepts. It looks kind of smooth and continuous, so it might be an x cubed. When we graph the derivative, it might then be a degree what? 2, because when you take the derivative by the power rule, you lose the degree. So it might be a parabola. Let's see. First thing we do is to look for the zeros, the horizontal tangents. That's going to be at -1 and 3. Okay? To the left of -1, my function is increasing, so my y values are positive. Okay, now I don't know necessarily, well, I guess we could do that right there. As I come down, my slopes are most negative right there at -2, perhaps. So I hit a low point, and then I come back up. And then it's going to be increasing after that. So it looks kind of like a parabola. And this point at 2 should kind of locate down there. So it's not necessarily a parabola, but it looks like a parabola. Okay, I'm analyzing the blue graph now, right? And I want to sketch a graph of its slopes. So on my blue graph, what's the slope there at -1? It's a horizontal tangent, so that's the 0. On the blue graph right there at 3, that was the horizontal tangent. Okay, so every time you're sketching a derivative of a function, you're analyzing its slopes, and you're plotting y values that represents its slopes. If I were to take the derivative again, it would look linear, and then it would look horizontal, and then it would eventually make its way to the x-axis. The more derivatives you take, the less curvy something gets. Okay, let's label that before we move on. F double prime. All right. Same graph, but now it's going to represent f prime. What we want to do now is sketch a possible graph of f, given that f of -7 is 0. This is what we did yesterday, those last 2 examples. We're actually now sketching a graph backwards instead of forwards, okay? Now it says f of -7 is 0, so we're starting right here at the leftmost point, which is the easiest way to do it. Now we're reading the graph differently, okay? Now the y values are the slopes of the graph we're trying to draw. So if the graph is positive, we go uphill. If the graph is negative, we go downhill. The slopes of this graph tell us how to go up and down, right? Because the slopes of this graph are the concavity. So where this graph is decreasing, we're concave down. And where this graph is increasing, we're concave up. So anytime the signs of the y values of the slopes change, we reanalyze. So here we go. From -7 to -5, we have our positive y values, so we're going up, and the slopes are negative, so it's concave down. So increasing, concave down, got to look something like that. And at 5, we have a horizontal tangent, so kind of make it go into horizontal. From -5 to -3, we have negative y values, so we're going down. We have negative slopes, so we're concave down. So just start going down, down, down towards -3, concave down. Something like that. Doesn't matter if you cross the x-axis or not. It's your graph. From -3 to -1, negative y values, so we're still going down, but the slopes are positive, so now it's concave up. And we curve it, so we get a horizontal tangent at -1 because that's the x-intercept. So far, so good so far. Here we go. From -1 to 2, positive y values, we's going up. Positive slopes, we're concave up. So that's increasing, concave up. Here we go. Right there at 2. I happen to cross the x-axis. All right, from 2 to 3, positive y values, still going up. Negative slopes, concave down. Just until you get to 3. Almost done. 2 more intervals. Here we go. From 3 to 5, positive y values, still going up. Negative slopes, concave down. Okay. From 5 to 7, still positive slopes. Notice I went horizontal here. Not quite enough. Go horizontal at 5. From 5 to 7, positive means increasing, concave up. Something like that. So we have a horizontal tangent right there at 5. There's what the graph looks like. Something like that. Something like that. Okay, now follow-up question. Typically, is it possible to determine the x value where the absolute minimum occurs? Definitively. Yes, the absolute minimum must occur where? At -1. Okay, is that right? I don't know. I'm asking. Why must it? Where else could it be? What are the other candidates? Bless you. The critical values of the endpoints really are the only places, right? So the only other option would be the left endpoint, which I'm thinking might be, I mean, if we drew it like this, of course, -1 looks like the obvious, but notice by the time we get to -1, the y values tell you that we're going up, and then we're going down. The way I drew it, I went a lot further down than I went up. Is that how it really went down? Or how it happened? When we start going backwards, we're going to be looking at areas. Let me show you that. It's another way to find your iPad. That's the only bad thing about being untethered. If you were to look at the area of this region here versus the area of that region there, and this is kind of a little harbinger of things to come. The areas tell you essentially how high, how much you went up and how much you went down. So if you want to know if you're actually lower at -1 than you are at -7, you would end up doing a quantitative comparison between these two areas. Those two areas look almost, they could be kind of the same, right? Or maybe you might argue that this one is a little bit bigger. So I don't know. Maybe I went up by the exact same amount I went down, and maybe at -1 I'm really just back down on the x-axis and not way down here. Or maybe I stopped just short of the x-axis if this area on the left is bigger. In that case, the left endpoint would be the absolute min. So you got to be careful when you draw things. I would say that the two candidates for the absolute minimum would be the left endpoint -7 and -3. But I don't think the other critical value at 5 is going to be the absolute minimum. Do you? Because to the left we have values that are lower, and to the right we have values that are higher. So he can't be really anything. So -7 and -1, I would say, are the candidates. What about the absolute maximum? Is that one definitive? Yes, I think that one we can say indubitably that this function would have an absolute maximum at x equals 7, without a doubt. Okay? Because if we start arguing about whether from -7 to -1, you know, they cancel each other out in terms of going up and going down, or we ended up lower, notice from -1 to 7, this function is monotonic increasing. So it's going uphill the rest of the time, and by the time we get to the right endpoint, it should be higher than any of that. Okay? All right. That's kind of big right there, because that ties in a lot of ideas that I could ask you on the multiple choice and, of course, on the free response. Blah, blah, blah. Kind of picking and choosing here. I'm not sure how much more I want to do. What time do we have to? Till 10:40? 10:35. Oh, man. Okay. Let's talk about the test bin real quick. All right? Make sure you know how to do all the stuff on the worksheets. Okay, and I would take a look at 3.5.2. I like this problem right here, just kind of an FYI. Maybe not that one as well as factoring out least powers. You know, when are we on cusp alert? Yeah, when you have fractional exponents that are less than 1. Okay, so if you have something like 2/3 and 1/3, you're on cusp alert. So they're going to be places that are critical values. So just drawing attention to that for no particular reason. And remember, when you have something like that, and we did examples like this, we got it down to a single factored, fully intact version of the derivative by factoring out least powers. That's the quickest way to get a single fraction, factoring out least powers. So make sure you know how to do that. Factor out least powers. That's like fractional powers. Okay, and the time that remains quickly here, your test is going to be 3.1 to 3.5. 3.5, the worksheet's not due. It's just kind of a summary of everything we've been doing. No calculator on this test. You're going to have, it looks like eight multiple choice questions. Oh, looks like, sorry, 10. There's 2 on the back. Oh, look at that. We'll call it 10. 10 multiple choice questions. Usually I have the back entirely free response. I made this last week, so it's been a while since I've looked at it. 10 multiple choice questions and 1 free response. Your free response is going to be an equation that looks something like this one, okay? You're going to have fractional exponents. And what am I going to ask you to do? I'm going to ask you to take the derivative. And I'm going to ask you to find the local extrema. And I'm going to ask you to verify. And then I'm going to ask you about concavity, which will require what? Second derivative. This is Corpy. Yes. I sure will. Okay. Mr. Painter, to the nurse. Your mom's here. I need to see you. Okay, your free response, as it sits right now, I give you an equation like this, and I'm actually having you manipulate it. So you're taking the derivative, you're going to factor out least powers, get it down to a single nice equation, and then, of course, you might have a numerator and denominator. You're probably already on cusp alert, right? You're going to find all your critical values, and you're going to test doing the number line with the first derivative, okay? And then you're going to tell me if there's a local max or a local min with that sentence. You will need the second derivative as well. So once you have the first derivative, you're probably going to have a quotient. You might want to do the Hody-High rule, and then you might have to factor out least powers again. And then I'll ask you some questions about concavity or inflection values, which means you're going to make a second derivative chart. So on this graph, on this test, I'm not going to have you make a sketch of a graph on the free response. You're actually going to be finding derivatives, doing more algebra, okay? But all the other stuff, like there's a multiple choice question here where I'm giving you a graph and I'm saying which one could be the graph of f prime or which one could be the graph of f. So what we just did will be more of a multiple choice question. All right, there's 3 graphs, 3 questions with graphs on the multiple choice, and actually the first 4 questions deal with the first graph. So there's a lot of questions where you have a graph and you have to interpret it, but those are multiple choice questions. Okay? So 10 multiple choice questions, 1 free response. On your free response, make sure you know how to do this. And if you go to your notes and you go to your worksheets, I think you'll have questions where we've done that. I'll be here tomorrow at 7 if you have any questions. Have a good day.